Hi, my name is Rodrigo Albuquerque. I'm Senior Lecturer in Physical Chemistry at Liverpool John Moores University, United Kingdom. All parts of this tutorial can be found at this homepage here. In this tutorial I have discussed parts 1 to 4, covering all these topics. And now, part 5, I will show some special topics very used in simulation. And I will briefly discuss Monte Carlo. These are useful references, in particular the book of Andrew Leach on molecular modeling principles and applications. These are the topics that will be discussed during this tutorial. Let's talk about the ensemble partition functions. We use the letter Q to express this quantity, and they are measurement of availability of states of a given system. Ensemble, we have seen already the definition of ensemble. If you don't remember, just go back to the part 4 of this tutorial. Ensemble is a collection of systems in thermodynamic equilibrium, each being in a different microstate I with total energy epsilon I. So this is a rough visualization of an ensemble. You can think of it as a collection of your snapshots of your molecular dynamic simulation or of your Monte Carlo simulation. So each system here is actually a configuration of the real system. So the real system has a probability to be found in this configuration of energy epsilon 1, has another probability to be found as this configuration where the energy epsilon 2 and so on. And if you have a finite number of particles, so we have a small system, we may define the ensemble partition function for the canonical ensemble, where the number of particles, which can be number of atoms, for instance, volume and temperature, they are constant. And this partition function is actually a sum over states. This sum is shown here. And we have the epsilon, the energy of each of these, we can call it microstate, temperature, and a Boltzmann constant. If you go to another ensemble, like the grand canonical ensemble, where now the chemical potential, the volume, and the temperature are constant, we can rewrite this expression, take into account the other parameters. Chemical potential shown here, number of particles with chains is not constant, temperature is constant, and so on. We have now the isobaric isothermal ensemble, where the number of particles, the pressure, and temperature are constant. So you can calculate the sum over states for the isobaric isothermal ensemble using this expression here, where P is the pressure. And if you think we would like to calculate the probability of the real system to be in any of these specific microstates, we can use again this partition function. Actually, we can use the partition function to calculate many thermodynamic quantities, as we'll see in the next slide. But let's suppose we have an NVT, the canonical ensemble. Let's calculate the probability of finding the system at a given configuration I with the energy epsilon I. We can just use the partition function of NVT. We see we have just the energy of this microstate I divided by the whole sum over states, which means divided by the canonical partition function. As soon as we get the partition functions, we can now predict a range of thermodynamic properties, like Helmholtz energy, Gibbs energy, internal energy, enthalpy, and a combination of them to generate other properties. We see here, in the case of Helmholtz energy, this calculation is straightforward. A is equal to minus K, T, so the Boltzmann constant, temperature, and the natural logarithm of the ensemble of the canonical partition function. So Q and VT. Depending on the property you would like to predict, it's much easier if you change to another ensemble. Like if you are interested in predicting Gibbs energy, instead of using the canonical ensemble, which has a very complicated expression to predict G, we can just change to the NPT ensemble. And so the expression becomes very simple to predict the Gibbs energy. And there are many different expressions. If you just go to any book of statistical mechanics, you can give a look at these expressions and how to interconvert them for different ensembles. Just to give a short example, I will not derive this here, but I will show where it has been derived. But the heat capacity, sometimes you would like to calculate this quantity. Heat capacity at constant volume is defined as CV equal to the first derivative of internal energy, U, with respect to the temperature. You can just, based on this expression here, use the expression of U shown here for the canonical ensemble. The chain rule, so some knowledge of the chain rule is necessary, and the fact that the expected value of the internal energy is simply the average of the total energy of the system. So when you calculate the average of the total energy of your system, you just can use inside this expression to get the CV. And how to predict this expression here from these two, this and this, you can see at page 348 of the molecular modeling book of Andrew Leach. But many such properties can be derived just based on the partition functions and on the expressions for different energy terms. Many force fields use the so-called united atom approach. This approach, light atoms are implicitly considered. For instance, we have hydrogens here in this methyl group, and these hydrogens just disappear, but they are still implicitly considered inside this new atom. I'm symbolizing as a C, but the mass actually increases a bit, and the parameters are slightly different, so that it takes into account the hydrogens without explicitly simulating the hydrogens. The main reason to do that is because one saves computational time. For instance, all terms of the potential energy involving hydrogens will disappear. So we don't need to compute many interactions involving the hydrogens here. Also, the vibrations involving hydrogens, the stretchings, also all these interactions, they just disappear from our simulation when we use a united atom approach. As a consequence, time step may increase, so you can just use a slightly higher time step, because now you don't have the carbon-hydrogen stretchings, which have very high frequency. In general, you need to keep your time step small, but as soon as you get rid of the hydrogens, you can now increase a bit time step. So the same simulation now needs fewer steps to run. So it saves computational time. Here we see a simple molecule, hydrocarbon, and all hydrogens are shown here, but now you just represent, using the united atom representation, you would have only 3 atoms here. This is not properly an atom, but this is a kind of atom having a heavier mass. And if you think about the interactions, when you see 2 molecules coming together, they are close, and they are, for instance, the carbon atoms are at a distance d, because of the repulsion involving hydrogens, for instance. When you use the united atom force field, united atom approach, there are no hydrogens anymore, but the distance d should be precisely the same because we are simulating the same molecules, just the representation of the molecules is changing. So we need to take care that this distance remains the same. To achieve these results, effective parameters are used associated with these heavier elements, conserving the same previous total mass. So the mass of all hydrogens are still here, and are still here, and are still here. And in the end, we get the same distance between these two groups. For example, there is one united atom force field shown here. It's called New Generation Amber United Atom Force Field. It has stretching terms, bond bending, torsion, van der Waals, and electrostatic interaction terms. It can be used to describe protein folding and protein-protein binding. There are many other united atom force fields available. Let's move a bit in the subject. We can use, now we can describe a little bit of coarse-grained methods. This is actually a similar idea of united atom force fields, but it uses beads. Instead of putting hydrogens in the same locating at hydrogens at the same atom, we put now many atoms together to form a bead, a very massive bead. For instance, let's see this molecule. There are many atoms here, and we can see or identify perhaps some specific groups which are repeated in a molecule, which can have some importance. And these groups, we just substitute all atoms inside this. For instance, there's a purple region by one single bead. So in this case of this molecule, we would have 4 beads. Each bead is just a sum of all atoms. And when we use a bead instead of all atoms here, we are not describing a stretching, for instance, carbon-hydrogen stretching or carbon-oxygen stretching or torsions. We are not describing many interactions inside. So we are simplifying the system. We of course lose a bit of information. And we can represent, for instance, this whole molecule by 4 beads. And the distance between the beads needs to be parameterized, so that the distance between the center of mass of the green bead to the center of mass of this blue, or here is a little bit purple bead, should be the same as when we just use the all atom force field, for instance. When you consider all atoms, so this distance should keep the same, so that you have some physical meaning. Still, you lose a bit of meaning, about a little bit of physical meaning when you remove so many atoms, but you still can keep some information. And now, when we have 4 beads, each of them is a very massive, we can now make a material. We can make an aggregate or any surface or anything. We can put many such molecules together. And now we are using much less atoms to describe this system than we would use if we would be using an all atom force field. Now we have many beads, and it's much easier to describe, for instance, phase transition. Phase transitions much easier, basically because now we have long time simulations, which means we don't have now stretching carbon-hydrogen stretchings which have high frequencies. So we have very heavy mass, have heavy beads here, and the stretching involving beads has a low frequency. So you can use a very large time step, like 20 to 40 femtoseconds in the case of the Martini force field. And we are not only saving computational time when we use a very large time step, but also when we use much less particles. On the left side, we have many atoms, or we can call it particles, and on the right side we have much less particles. So in fact we can use the same number of time steps of a simple simulation, we can describe phase transitions. And of course we can, as soon as we have described the phase transition using this coarse-grained method, it's possible to substitute the bits by the atoms again, just to gain again to get some local information, to extract some local information here. So it's possible to go to the right side and to the left side. Now let's talk about solvent models. Here I describe how to explicitly consider the solvent in your simulations. But of course you can make implicit consideration of solvent. One of the ways to do this is by just using the appropriate epsilon parameter in the electrostatic terms. If you want to simulate a certain interaction in water, you just put the epsilon of water in the electrostatic terms. So water molecules, for instance, they are very often used as a solvent, and we can consider the geometry frozen, which saves a lot of computational time, but it can still make hydrogen bonds with the solute, with the molecules, that is water is solvating. And we can consider the water molecule as freely vibrating. So here you have stretchings, we have bending of the angle, of the bond angle. This is very expensive, the second option. So in general, many people just go for the first option. The geometry is frozen, and it's possible to do hydrogen bonds between water molecules or between the water molecule and the solute. And so I show just the frozen geometry models here. First one is tip 3-point charge model of water. Here we have this bond angle is the same and is kept frozen, and this bond angle is kept frozen and this bond length is kept frozen, and they are the same, this and this. And here we have the angle and the bond length frozen during the whole simulation. Now we add partial charges here, located at the oxygen and at both hydrogens, and notice that the total charge is 0 because the water molecule is neutral. And the electrostatic interactions would involve all 3 partial charges. So the oxygen and both hydrogens would be participating in electrostatic interactions. But the van der Waals interactions would be described by a Lennard-Jones function centered on oxygen only, which means oxygen is the only atom participating in the van der Waals interactions, which again saves a little bit of computational time. These parameters, they can be optimized by trying to reproduce the density of experimental density of water. For instance, if you simulate a whole box of water, like 5,000 water molecules inside your box, simulation box, you try to change these parameters until you get as close as possible to the experimental density of water. So you can also propose a different model for the water. Here there is a second model called ST2. Here there are 4-point charges. 2 of them, these black points, are just simulating the lone pairs of the water molecule. And again, the geometry is frozen. So this bond distance is the same as this here. This distance is the same as this, and the angle theta is constant. In this case, the oxygen has no partial charge. So the oxygen has a charge of 0. Here we have slightly different parameters for the angle and for the both distance shown here. And during the simulation, all the time is frozen. So no internal degrees of motion. Now, the electrostatic part involves 4 points. Involves these partial charges, which represent the lone pairs of the water molecule, and involves both both hydrogens. And the total charge again is 0 because the water molecule is neutral. The electrostatic interactions would involve then these 2 atoms and these 2 charges. But the van der Waals interaction would be described only by considering the oxygen. So we use a Lennard-Jones function centered on the oxygen only. So we also save a little bit of computational time, not only by freezing the geometry, but also by not considering van der Waals of the hydrogens and of the point charges. There are also other models for water, for instance SPC, TIP4P, BF, and so on. You can also find in the literature different models. In these models, they save a lot of time. If you need to solvate a very big protein, for instance, you need to use many water molecules, and if you just are freezing the water molecules as we are shown here, you can save a lot of computational time. In this example, in this paper, I have used the SPC model to solvate a clay. Actually, they are the internal layers of water of the clay. I think here I used 730 water molecules. The whole details of this molecular dynamics simulation, the models I used, is shown in the support information if you are interested. Let's try to predict the properties of macroscopic systems. Let's imagine we have a macroscopic system here. It's the water on the right side, and we are trying to represent the macroscopic system by few molecules, showing on the left side. Can you predict macroscopic properties by just using few molecules? The molecule in the middle, this here, is completely surrounded by others. Not completely, but actually there are 6 water molecules here around this central water molecule. But how about the ones at the borders? So this water molecule here, for instance, is only surrounded by 3, has only 3 neighbors. On the other side, this side here is empty, so there's vacuum. This doesn't represent the real situation, so this is not realistic. If you just go inside to this macroscopic sample, you would realize that every single water molecule is completely surrounded by other water molecules. Not only by 3, as we see here, but perhaps by 9, 10, or 12. We may think of another problem here. Let's imagine we have temperature fluctuations or collisions or any other process, and which just ejects this molecule here. So this molecule will get lost. It just leaves this water cluster. So when you leave, you are just destroying your system. And we need to prevent this from happening if you wish to get some properties out of these water molecules, out of this very small system. So how to solve this problem? First of all, we should put all molecules inside a box. If we make that, no molecules will get lost. Second, we replicate the box in all directions. So these are the principles of periodic boundary conditions. Here we can see a cartoon showing the simulation box, which is the central box here, containing the molecules or particles, containing the system to be simulated, and is completely surrounded by other boxes. In this case, we have 3, 6, 7, 8 boxes here, but we have many more, as I will show later. We have 2 things here. One is that this blue ball, for instance, this can be a molecule, for instance, when it leaves this central box, another one on top of this box would just enter this central box, so that everything, all atoms in the central box are doing is repeated by the atoms inside this, the repetition boxes, or the copies of the central box, so that we don't lose atoms. And we also avoid border problems. Because, for instance, if you think about this molecule here, if you only have the central box, this molecule would be interacting with these other molecules here, but it wouldn't be interacting with these molecules here. But as soon as we use the copies of the central box, we make sure that this molecule is now interacting not only with these molecules here, but it's also interacting with the other ones here. So that the same molecule is now completely surrounded by other molecules. So that this brings us closer to the macroscopic situation. So there are not only 8 not 8 copies of the central box, but we have actually 9 plus 8 plus 9. In the same plane, here we have 8 boxes, but you can just imagine this plane is this green box belongs to this plane, the central plane. We have also 9 boxes above this central box, and 9 other boxes just below it. This central box would be just, you cannot see here, but it would be in the middle of this cube. So that in fact we have 9 plus 9, 18, plus 8, 26 surrounding boxes around the central box. This of course increases computational time, but it solves other problems. This box, as you see, is a cube. It could have many other shapes. Which shape is better? This depends on the symmetry. If you are simulating a spherical protein, for instance, you may use another box like a truncated octahedron, and so on. I'll show in the next slide the different shapes. How many molecules should I add to this box? This depends. If you are simulating a solution, what's your concentration? How many solutes you would like to add to have a certain concentration? If you are just simulating solvent, what's the density of your system? So you need to add a certain number of molecules. So it depends. In each case, you can use a different number of molecules inside. And how big should be my box? This actually depends on the interaction range. For instance, if you have only van der Waals interaction, van der Waals interactions are short-ranged, while electrostatic interactions are long-ranged. So this would say if your box should be a little bit larger, to take into account these long-range interactions, but there are also other methods to treat this, as I will show later. Or if this box should be slightly smaller. But this also depends on the convergence. So if you want to predict the density of water, you could try to make a simulation box using just, let's say, 50 water molecules and see what happens. Can you reproduce the density of experimental water? If not, you can just increase to 100 water molecules or 200 and so on, so that you can have a larger box actually. So these two things here, how many molecules and how big should be my box, they are actually related. There are different types of boxes. Here you see a cubic box, hexagonal prism box, truncated octahedron, and so on. So you can choose a different box to simulate your molecule and to use a periodic boundary conditions. But let's see the case of a spherical molecule. Let's suppose you have a solute, could be a protein, for instance, and you need to embed the solute in a water layer. So you need to add many water molecules. You need to add the solvent around the solute. You can use, for instance, the cubic box, this cubic, and the octahedron, truncated octahedron box. When you put the solute inside the box, you need to fill in the space the empty space with the water molecules. Now, if we are using a cubic box, you see here in yellow, you need many more water molecules to fill this box. While if we use this truncated octahedron, shown in red, we need much less water molecules. So your simulation is faster, is much faster if you use a truncated octahedron, because you save a lot of computational time. That's why in some cases, if you have a spherical solid, it's much better to use this truncated octahedron instead of a cubic box. The Ewald sum can be used to calculate the total electrostatic interaction energy between charges. So in this case, we have two charges, but remember you can have thousands of atoms or thousands of charges here. In this case, you have a box, simulation box of size L, and you need to compute the interaction energy between these two particles. But when you use periodic boundary conditions, we have actually many replicas of the central box around this box, around the gray box. And you can calculate now the total electrostatic potential energy, let's call it U, involving one central simulation box, the gray one, which has a length of L, and all replicas around it. So we have this expression here, the product of charge divided by the distance. This is a long-ranged interaction, since you need to increase a lot this R in order to produce a very small interaction energy. So in general, we need to consider very large R's to converge this series. And the terms I and J are excluded inside central box, so I'm not computing the interaction between the red point with itself or the blue charge with itself. Okay, so positive and negative terms of the series are not convergent. So they are actually conditionally convergent, which means convergence can be achieved depending on the order that you add up the terms. This Rij, the distance between one particle to the other, it's shown here, which is this quantity shown, this expression. Now you have this distance from here to here. I'm showing a vector, but actually you can put here the distance, which is L. And now if I sum this vector with this, I'm getting the vector from the red particle to the blue one of the next box. You see, to compute the interaction between this negative charge located at the central box and the positive charge located at one of the replicas. So now we have here the distance between these two can be given by the module of this sum of these two vectors here. In practice, to get a convergent number, which means to get a constant value of U, we need to consider many replicas around the central box. And this can be very computationally demanding. In general, it's possible to make a spherical sum, which means we just consider a cutoff of n. N is a vector, position vector of different replicas around the central box. And we can consider specific thresholds or cutoff for n. Let's say n equals 1, 2, 3, 4 boxes in this direction. So, but just remember this should be a spherical sum, which means you are only showing here 2D, but actually we have 3D, three-dimensionally distributed boxes around the central one. This method is only accurate for very large cutoffs. So if we increase a lot the radius of this sphere, we can actually converge the series. So this convergence is very slow. And we should not forget, this is a long-range interaction. So this is the main problem here. And we can take we need to take a lot of computational time to compute this interaction, the electrostatic interaction involving the central box and all replicas around it. So this expression can be slightly modified as I show in the next slide. And the computation scales as n cutoff to the power of 6. So if you increase a lot the number of replicas around the central box, you are increasing the computational time by a factor of 6, the power of 6. So you actually spend a lot of time just to make this computation. One way of solving this equation, solving this expression, is by recognizing that 1 divided by r, so here we have distance, the denominator. We can simplify this, or actually expand this expression 1 divided by r can be expanded in this form, where we have used a function of r divided by r, and here 1 minus the same function divided by r. Which function would be this f of r? So it's one use the complementary error function of r multiplied by a parameter alpha. Now this complementary error function is given by this expression. So for given x, we just need to solve this integral. Put the x value here. This alpha is actually Ewald splitting parameter. This actually is related to the Gaussian, the weight of the Gaussian distribution that I will show now. So we have to use Gaussian distributions of charges centered in each charge of our system. So just remember, in our previous slides, we had in the central box one positive charge and one negative charge. So in each one of them, we need to center a Gaussian distribution of charge. And this Gaussian width is alpha, which is the Ewald splitting parameter, which used in this complementary error function, which is used to expand this expression here. So afterwards, we apply this on this expression and expand and get different terms. And now coming back to the charges. Originally, we have one in the central box. We have one positive charge. That's why the bar is going up, as blue is +1, and we have one negative charge, -1. The bar is going down. And this original interaction is long-ranged, because interaction between these two charges is just the product of the charges from here divided by the distance between them. So we need to increase a lot this distance in order for the interaction to decrease, to be neglected. So this is a long-range interaction. But what we do now, we just add a Gaussian distribution of charge located at the same position of the original positive charge. But here we are adding a negative charge, actually a distribution of charge surrounding this positive charge. Of course, we are changing the total charge here, but we need to correct this afterwards. And we do the same with this negative charge. We place here at the same location a positive charge, actually a distribution, a Gaussian distribution of a positive charge. So that's this charge, originally with -1, is completely surrounded by a charge distribution of the opposite sign. So now, when I try to compute the interaction between these two original charges, +1 and -1, this interaction is not long-ranged anymore. Now it's short-ranged, because these extra charges here they are just screening this interaction. So now we have screened interaction, which is now short-ranged. And this is done using the real space. I will show this in the next slide. Now we have to rebalance the total charge, which is done in reciprocal space, which means I need to add another Gaussian here of positive charge, because I just add one negative charge here, and I was modifying the charge, total charge of the system. Now I'm correcting this added charge. And the same here, I previously added the positive Gaussian distribution, and now I added negative charge distribution here, just to correct the total charge. So if you sum all these numbers here, you see that the total charge is the same as previously. By adding these Gaussians and using the real space and the reciprocal space, we can come to the Ewald formula, which shows that the electrostatic interaction involving the central box is given by four terms. The first one is corresponds to a short-ranged interaction in the real space. The second one is the reciprocal space. And you have also a correction for the interaction of a Gaussian distribution with itself. And the last one is related to the medium surrounding all boxes. So the external, what's outside all the boxes. Is it vacuum? If it's vacuum, we need to correct for this interaction here, adding this dipolar term. We have then the sum given by four terms. The first one is carried out on the real space. The second one is the reciprocal space. And the last two are corrections. The first one is a real space contribution to the potential energy, the electrostatic potential energy involving the central box and all replicas. I just substituted that function I showed in the previous slide by the complementary error function, which is now shown here. This alpha is the parameter that gives the width of the Gaussian charge distributions. Now, the complementary error function of a large number tends to 0, so it can become very small, which means if you choose this alpha as a large enough number, this sum will be truncated into just the first value of n, which is 0. N equals 0 means I have just the central box, and there's the minimum image convention. In this case, I use a cutoff which is smaller than half of the length of the box for cubic box. And then just remember this part of the interaction, electrostatic interaction, which is done in the real space. This is now a short-ranged interaction. It's not a long-range interaction anymore, because I was using the Gaussian distributions as I explained in the previous slide. The second term is the sum in the reciprocal space, is actually a Fourier transform. And this is a reciprocal space contribution to this potential, electrostatic potential energy. And this is, you can use the K. The space for the K is given by the 2 pi n is a vector from the central box to the next, to the replicas, and L is the length of the simulation box. So we have a sum over K vectors, and we can use also cutoff for the K. And we have now alpha, the cutoff for the radius, for the real space, for the real part of the computation, and the cutoff for the K vector for the reciprocal part of the computation. We have 3 parameters. These 3 parameters are adjusted or optimized actually when you run a calculation. You can choose the standard values, or you can actually use your own. Now the third term is a correction to prevent the self-interaction of Gaussian distributions. The Gaussian distribution I just showed in the previous slide. The last one takes into account what is surrounding all replicas. So if you have a conductor surrounding all replicas, you have infinite for the epsilon. In this case, the dipolar contribution, the dipolar correction is 0. So if you have a very large number here, you have this giving 0. But if you have, for instance, a vacuum or any non-conducting a material surrounding the replicas, you need to put the epsilon here to make this dipolar correction. And then when you apply all these terms, you now are computing the electrostatic potential energy with the central box. In this case, UK scales more or less with n to the power of 2. It's much faster than I showed before, but it's not fast enough for many purposes. If you have a very large system with a very large number of particles, you may have a very large number of computations, and this takes a lot of computational time. So in practice, we use a fast Fourier transform to, for instance, to compute the electrostatic potential energy involving the central box and the replicas. In this case, this scales with approximately with n, with number of particles or number of charges in the system. But this is much faster. And one of the methods, for instance, is called particle mesh Ewald, PME. It's very famous, PME. And this consists in putting a grid of charges over all atoms in your system. And from this grid, you can compute potential energy and the forces acting on all atoms. In order to calculate electrostatic and van der Waals interactions, we need first to know which atoms are close enough to a given specific atom. So we see here cutoff radius. The red atom will interact with all blue ones, but will not interact with the black and the gray ones. Actually, it can, in the real situation, it can interact, but the interaction is so weak that we can neglect. That's why we use a cutoff. But in order to know if for instance, if this black atom is close enough to the central red atom, we need to compute the distance between the central red atom to this black atom. And in fact, we need to compute all distance between all pairs of atoms inside the system. You can imagine if you have hundreds, thousands of atoms, this can take quite a time. So one way to solve this problem, to increase the efficiency of this of the computation of the electrostatic and van der Waals non-bonded interactions, is by the use of a neighboring list. So we make a list of all neighbors of each atom in the system. In this case, I'm showing all neighbors of this central red atom. Actually, we see the blue ones are the immediate neighbors, which means they are at a short distance, a distance shorter than the cutoff radius, which means the interaction between the red one and the blue ones will be computed. The non-bonded interaction will be computed. But the black ones should be also checked every time. So we make another circle. This is a neighboring line. So inside this neighboring line, we also keep checking for every single time step the distance between all these atoms to the central red atom. Because they are more or less close to this cutoff radius, sometimes during the simulation they can go inside, so you need to consider this black atom to compute the electrostatic and van der Waals interaction. But we only check the condition that the distance, if the distance is larger than the cutoff, for atoms inside the neighboring line. So just the black ones which are inside this blue line, we need to check the distance to the central one. So that we can ignore actually the gray ones which are outside this neighboring list. This saves a lot of computation time. But we don't do this for a very long time. Actually, we run 10 to 20 simulation steps, and in each step, we can now compute the van der Waals electrostatic interaction, and we can compute also the distance between the central red atom and all atoms inside this blue line, just to know if the atom is close enough to be inside the cutoff or if it's slightly outside the cutoff, so it will not be computed. But then when you do this, we can calculate electrostatic and van der Waals interactions in a much more efficient way. This saves a lot of time. And then we make a new list, which means we update the neighbor list to see which atoms are now inside this blue circle. And then we keep repeating steps 1 to 3 through the whole simulation. This is a way to save a lot of computation time, to avoid having to compute all distance between each atom pairs inside your system. Radial distribution function calculations are very often used in simulations. And the most common such distribution function is the pair distribution function, which measures the probability to find a pair of atoms at a distance r from each other, with respect to the probability found for the system of the same density but having atoms randomly distributed, so that we compare the probability of finding two atoms apart at a certain distance r with the probability of an ideal gas, so that if you see any structure in our system, we are completely sure that this structure is real, because we are just comparing with the ideal gas, which has atoms completely randomly distributed. We show here a GR, the pair distribution function, where we have at the center, we have this blue atom, and we can be monitoring, for instance, oxygen-oxygen distance or hydrogen-hydrogen distance. So we can just, or oxygen-hydrogen distance. Actually, we can specify which distance we are talking about. Is distance between two oxygens, or distance between two hydrogens, or distance between one oxygen and one hydrogen. And we can see that having this atom at the center of the sphere, we see how the probability changes upon increasing the distance. So we see here that very close to the central atom, we have a high probability of finding these other atoms. That supposes the atoms we would like to investigate. Let's say all of them are oxygens, and we are trying to make the pair distribution function between oxygens. So this R would be the oxygen-oxygen distance. And we see very close, there is a high probability of finding other oxygens. And then the probability goes down and then goes up again, so that you have a certain structure, showing that at a certain distance, you have high probability of finding atoms. One can use many different atoms at the center. So here we are using, let's say we are investigating the radial distribution function, actually the GR, between two oxygens. So I'm showing just how to put this center of this sphere at this blue atom, this oxygen. But we could also make the same using another center, like this here, or like this here. So in fact, when I show this function, when I show this distribution, this means that I'm using different centers. For instance, if I'm talking about oxygen-oxygen distribution functions, we are repeating this plot for many different centers. So many different central atoms. I'm just showing for one here, but this is a very powerful statistic quantity. And one usually use two atom types, like atom type 1, atom type 2, or type 1, type 1, type 1, type 5. So you can just choose. I'm talking about oxygen, but if the oxygen has assigned an atom type, we could just say this is the RDF or GR, the pair distribution function involving types 1 and 1, 1 and 5. In general, you give this information to the programs to generate this curve. But just remember, when you see this plot, this involves many central atoms, not only this here that I'm showing, but all the others are also quantified. We can also use different snapshots to produce one single RDF curve, like this here. So we are doing a simulation, and we just collect many XYZ coordinates of the atoms being simulated, of the system being simulated. And so you'd have many snapshots, snapshot 1, 2, 3, and 4, and so on. And then we can take into account all snapshots. So actually, this curve would be the average of these individual RDFs of each snapshot. So this is in fact a very powerful statistical quantity. And just remember, in each curve, you may use different central atoms. So it's really a powerful statistical quantity. We can also use RDF curves to compare with the experimental data. It's a way to characterize the systems we are simulating. Because from the experimental point of view, we can measure X-ray diffraction peaks. In the diffraction peaks, they can be compared with the RDF curves. So producing a radial distribution functions is really useful to help characterize the material. But you can also use these curves to predict properties, thermodynamic properties. For instance, the total energy of a system composed of any particles, and assuming the real gas, is given by this expression here, where you see that we are integrating over the curve of GR, shown here. Of course, multiplying by other parameters and integrate from 0 to infinite. And then we can produce actual thermodynamic properties. So knowing how to do radial distribution functions is very, very useful and very important for basically every kind of simulation. Just to give an example, we see here a gold nanoparticle. It's a truncated octahedron simulated at 300 Kelvin. So we have this distribution function showing the distance between two gold atoms. This at 300 Kelvin, we have a very organized structure, but when we heat up the system to, for instance, 1400 Kelvin, we just get a phase transition, and now the system is melted. And now the function, the radial distribution function, can be very different. First of all, the peaks are wider here. They're not so sharp as before, and we may have less peaks, showing that there's not so much order. We have just a short range order, but not a long range order. So this is maybe similar to liquids, where you have only short range order, but not long range order. While in this case, we have a long range order too. The first peak, this peak would give the first coordination sphere. So it represents all atoms immediately close to any central gold atom. The position shows the mean distance between nearest gold atoms. So in this case, most gold atoms are on average about 2.8 angstroms apart. The area gives the number of neighbors. If you have infinite crystal, we have infinite sharp peaks. We may have very sharp peaks, and this goes up to infinite. Applying constraints and restraints is very usual in molecular dynamics simulations. This allows for saving time, computational time. We may apply constraints, which means certain values are fixed, so certain groups of atoms are frozen. There are no degrees of freedom. While we can also apply restraints. The restraints are certain variables are encouraged to have certain values. So there are still degrees of freedom, but the atoms are fixed to a range of coordinates. A small penalty can be applied so that the atoms would possess a range of coordinates. This can be better explained here. Typical constraints and restraints are shown below. So we can freeze CH bonds so that the bond distance is frozen during the whole simulation. The vibrations are not occurring during the whole simulation. So we can change our time step from 1 femtosecond to 2 femtoseconds. So we can, using the same number of steps, simulation steps, we can have a longer simulation. We can save computational time for the same simulation time. We can also freeze OH bonds in water models, as I discussed in the previous slides. And these two first ones are constraints, because parts of the system is completely frozen. The third one is a restraint. So we can keep a certain bond length in the range, for instance, 1.5 to 2.5 angstroms. The bond distance would stay in this range. If it goes out of this range, penalties, energetic penalties would be applied. There are some algorithms to apply constraints and restraints. One well-known algorithm is called shake, which modifies the equations of motion, for instance, the Verlet, solving it sequentially for each constrained part. So you can constrain a bond, an angle, a torsional angle, iteratively. And one uses a tolerance criterion in each case, since one constraint can violate another one. There is another algorithm called Radial. In this case, the equation of motion are modified by using the velocity Verlet integrator. You can just go to the bibliographic literature I'm citing this tutorial to learn a little bit more about these algorithms. Molecular dynamics can be used to help in energy minimizations. In this case, I will show how to combine steepest descent method. Actually, you could use any other minimization method. So in this case, I'm using SD with high temperature molecular dynamics to explore the conformational space or phase space of a given system. So let's imagine we have a system full of local minima and one absolute minimum here, which is very difficult to find. And then initially you draw your system. So you put the atoms, you draw all atoms or molecules so that you have an initial gas, which will not have a very low energy. So you have your initial gas. Actually, it's not even in the bottom, is not even a local minimum, but it would be a little bit higher. If you make an initial optimization, it would go to the local minimum. But okay, let's take this initial gas and we make a molecular dynamics at let's say 500 Kelvin, which is a very high temperature. We introduce many degrees of freedom. Rotations can occur. We have a very strong diffusion, molecular diffusion if you have molecules in your system. And we have access to a broad surface, energy potential, energy surface. And now we run this molecular dynamics at 500 Kelvin for a long time. And every, let's say, 1 picosecond, we take a snapshot and we do steepest descent minimization on that snapshot so that we can fall in a local minimum. In this case, we make a minimization, this snapshot, after 1 picosecond of molecular dynamics to produce the structure number 1. So we can get a local minimum. And we wait a little bit more time. After 2 picoseconds, we get another minimization. We do another minimization to produce another structure. I'm calling structure number 2. And we can repeat this. After 3 picoseconds, we can get another local minimum. And 4 picoseconds, we have another local minimum. Eventually, we could get the absolute minimum. This is not guaranteed. It's very difficult to get an absolute minimum. But for sure, you can generate a series of local minima, which are very useful to explore your conformational space or phase space. In general, the result, the program can actually keep all conformations generated, conformation 1, 2, 3, 4, 5, and so on, or just keep the lowest energy one. So you can, if you can run this molecular dynamics for a long time and make as many minimizations as possible, you can perhaps get the absolute minimum. But this is a very useful method to help in energy minimization. Simulator annealing is another technique which can be used to find a local minimum. Eventually, it's possible to find an absolute minimum. In this case, we have again our initial gas. We make a molecular dynamics at a very high temperature, let's say 1400 Kelvin. And we equilibrate the system at this temperature. And after a while, after the system is more or less equilibrated at this high temperature, we cool down the temperature very slowly. So we decrease the temperature in a very slow fashion so that it may possibly find very low energy minimum. I'm showing here as if it were finding the absolute minimum, but there's a possibility. In general, it's very difficult to find the absolute minimum because you have hundreds of thousands of local minima and just one absolute minimum. So the system is cooled down very slowly so that there is a high probability to find a low energy minimum. So this is usually done in the simulator annealing. And I actually have done this to a nanoparticle of palladium nanoparticle. And you can see even cooling down for only 10 nanoseconds, it's not such a long time. It's possible to get a very similar structure. In this case, we have a truncated octahedron. At 300 Kelvin, we have a very good structure, highly symmetric structure, 1200 atoms. And after 1 nanosecond, the particle is molten at 1400 Kelvin. And if you cool down slowly from 1400 Kelvin to 10 Kelvin, during, in this case, 10 nanoseconds, it's possible to get a very good, highly stable structure. So low energy structure, as you can see here. If you have more interest, just read this paper. I think this is in the support information. I will briefly discuss the Monte Carlo technique. So first of all, this name came from the region Monte Carlo, which is very famous for gambling. In the gambling casinos, we use a lot of dice, so random numbers. So there's a central idea of Monte Carlo techniques that is based on random numbers. And different algorithms can generate these random numbers. We can use a seed number, which is just a number used to help in the generation of random numbers. They can be generated in any range. They can be positive or negative. So we can just make small transformations, multiplications, small operations with the random numbers to generate any range, positive or negative numbers. Just remember the assignment of velocities in molecular dynamics methods. I have discussed this in one of the parts of this tutorial, perhaps part 3 or part 4. You can check later. And these random numbers can be used to decide how an atom can move, which means which direction and distance, and also whether that atom can move. So is it allowed to move or not? So let's think of an atom having coordinates x, y, and z, and there's also an energy associated to this position. So this configuration has an energy associated to it, but I will not discuss the energy. I have discussed already in the previous parts of this tutorial how to evaluate the energy of molecular systems using force fields, for instance. But then we use the dice, we throw the dice to see where this atom is going to move, and we have now a different position. So this atom has moved to a new coordinate x, y, and z, to a new position. And these coordinates, they are associated to a different energy. So is a new position okay? So is this atom allowed to move and to be at this position? We have to throw the dice again, which means we have to generate random numbers again to answer this question. The answer can be yes or no. In case of no, we have to discard this new position, and we go back to the old position and we repeat this process again. But if the answer is yes, we just keep the new position and we repeat the same. We generate new positions, but starting from this new position. The first step to use the Metropolis algorithm is to generate new positions. So we first generate random numbers, lambda, in the range 0 to 1. These random numbers will be used to get new positions. So the new x coordinate equals the old x coordinate plus 2 lambda minus 1 multiplied by the maximum variation. This is a parameter, could be 0.01 angstroms. And of course we need to repeat this for all coordinates independently of the previous one, which means we generate 3 different lambda random numbers here to change x, y, and z coordinates in different ways. Now, lambda is different for every time. As I said, one can move one or more randomly selected atoms. I'm not going into detail here. And finally, we have our system, which has an energy, potential energy, V1, and then we generate new coordinates, which means we move atoms here. We have the system in a different energetic configuration. So we can compute again the potential energy, which I'm calling potential energy 2. And now, if the new potential energy is smaller than the previous one, this new configuration is accepted. So we consider this new configuration when we are going to compute properties afterwards. So we just save the new positions. And then we repeat, we keep moving the atoms again. But sometimes the new energy, the new potential energy, is higher than the previous one. In this case, we can still accept, we can still save this new configuration. But we have to make a Boltzmann analysis. So to accept high energy configurations, which means the red shown here in red, we need to use this acceptance condition. We generate a new lambda, a new random number, lambda, if this random number is smaller or equal to this part here, the exponential of minus delta v divided by kt. So delta v is the difference in energy of these two, the second energy and the first energy of the system. So just apply this formula because this quantity here changes from 1 to 0, from 0 to 1. And we generate a lambda which is also in the range from 0 to 1. Now this exponential of minus this energy difference divided by kt, where kb is a Boltzmann constant and T is the temperature, it shows this variation. So if we have a very large change in energy, which shown here in this axis, we have a very small value for this quantity here. And here on the right axis is the random number generated, lambda, which is generated in the range from 0 to 1. Now, let's suppose, okay, so the region below this green curve is the accept region. The region above is the reject region. Now, we need to generate a random number, and if this random number falls underneath this green curve, we can just accept the configuration. If it's above this line, we can reject this new configuration. So this analysis is just valid for the case where the new energy is higher than the previous energy. Now let's take a point here. Let's suppose we have generated configuration B, which has the new energy is higher than the previous one. So in configuration B, the delta V, so the energy difference between the new configuration and the previous one is not so big as you see in the x-axis here. So it's very high in this green curve. So this exponential, when you substitute the delta V, the value is very close to 1. So when I generate now a random number, lambda, the probability that it will fall in this big region is very high. And the probability that this random number will fall in this small region is small. Which means the probability that I accept this new configuration B is higher, as you see in the blue region, than the probability that I would not accept this configuration. This happens because the delta V is very small. Delta V is small here in this x-axis. This exponential value is, this value is very close to 0, which means we are very high in value in the y-axis. Now let's suppose this new configuration, the delta V is large. So we just generated the configuration C, where the delta V over KT is 2.2, which means the new energy is much higher than the previous energy. In this case, we are more to the end of this green line here. Now you can see that the probability that the new random number, lambda, falls in this large region is larger than the probability that it falls in this small region. Since the region of reject is larger, much larger than the region of accept, the probability that this conformation C will be rejected is very high. Of course, it could still be accepted, but the probability gets smaller. If the new configuration, if the new potential energy here is much, much higher than the previous one, we are at the end of this green curve So basically each random number we generate will fall in the reject area, the reject region, which means if you generate much too high potential energies, it's basically rejected. So this is the core of this Boltzmann analysis for the Metropolis algorithm. If you liked this tutorial, please visit the other parts of this online tutorial on molecular modeling. Just go to this homepage or click on the links below. Thank you for your attention.